WindResist is a novel algorithm designed for the operators of fixed-wing unmanned aerial vehicles to help them correct against the wind. Fixed-wing unmanned aerial vehicles are gaining popularity by quite a bit lately, and they're honestly preferred over conventional UAVs for applications that require them to fly long times or long distances. They're used in time-critical applications like research, search and rescue, firefighting, and the military. However, the biggest adverse disturbance to UAVs, especially fixed-wing UAVs, is the wind. It's the one that causes the most crashes, the most deviations from planned courses, and other issues that prevent the missions from getting done. Fixed-wing UAVs are particularly susceptible because they're designed with long wings that try to get as much airflow under them as possible to generate lift. This also allows the wind to manipulate them a lot better. It's difficult to correct for wind, and I know this from personal experience when flying a fixed-wing UAV. These drones fly out of sight, and so they don't have a frame of reference to look at. Ground control systems, where an operator is getting their data from, can also be laggy and go through multiple links before they actually reach the operator. With ever-changing winds, it's difficult for an operator to work in these conditions. Current solutions for wind resistance often are not available for all fixed-wing UAVs. They might rely on specialized sensors like to detect the wind, or a particular layout of flight controller with more memory or more operating power. Others don't adapt to the wind. For instance, the industry standard mode, RD-Pilot's acro mode, is designed to just hold control inputs constant. Again, with a constantly changing wind, this is not a good solution, or it's not a permanent solution. Finally, the most common method of wind resistance, and the one that is studied the most, is path planning. This is where an operator puts in waypoints beforehand, and a trajectory is planned that allows the drone to hit all of those waypoints. However, this doesn't work in all situations. A search and rescue operator might have something catch their eye and want to circle in on an area. The knowledge and expertise of an operator needs to be taken into account. They need to fly their plane. Other than that, also some limitations exist because it's a flight controller and it has limited time and computational resources. So this algorithm tries to minimize the angle between the desired yaw, desired by the operator, and then the actual direction that the plane is going. The desired yaw is interpreted from the controller's RC inputs for roll. They put in inputs for bank angle, and then the algorithm, using kinematic equations, determines their actually desired direction. The actual rate is determined by GPS sensors. And taking in sensor inputs has a lot of error associated with it, so those are also smooth using algorithms. In order to minimize error, fuzzy PID was selected because fuzzy PID minimizes error, but also prevents overshooting, and which is something that PID is very known for. When tested in Simulink, nonlinear fuzzy logic controller, like a Sugeno style, was found to reduce overshoot by 50%. And that is in the measurements below for this particular case and model. Next, a fuzzy lookup table was implemented just to minimize the amount of time that the algorithm has to spend searching through it every single time. The PID was tuned and found values for it using the math proxy simulation. And the math proxy simulation simulated wind through wind data taken at different altitudes, constantly changing, found in a real location. This was run off of the software that was written for RDPlane, and the algorithm runs significantly faster than an existing wind adaptation algorithm that actually takes in the wind and adapts to it. It also has significant improvement over the existing way that RDPlane corrects for the wind. The pictures on the left of mode acro are the way that RDPlane currently handles the wind. And with WindResist, it shows how much better the plane reacts to the wind and doesn't get diverted off course. There was no planned course for these planes. It was just RC inputs. So this system is designed to collaborate with humans. This is a very different way than a lot of other wind resistance algorithms have approached it. It's also trained on changing wind conditions, not assuming that wind is going to be constant in any way. This is capable of being deployed on any fixed-wing UAV that has a compatible flight controller, so one that is able to run ArduPilot, which is the vast majority of flight controllers. It also prevents disturbances due to wind.